Hi everyone. Can you please confirm if I'm audible? Just let me know. Okay, once you confirm, I will start. Hi everyone. So welcome to the class. Okay, so let's start with the binary tree discussion. So today we will see binary tree PYQs. Okay, gate PYQs. So most of the PYQs we will see. So, by the way, this class is for both the students which are preparing either for Gate CS or for Gate DA. So, if you are preparing for the Gate DA, then also you can attend this class. Okay. So let's get started. Now, basically, we will be starting a series where I will be not only solving, binary tree PYQs. So in this series, we will be solving most of the algorithm and data structures PYQ. So let me just tell you that what we are going to do in this series. So we are going to, let me write it. So we will solve most of gate CS, DA, data structures, and algo PYQs. Okay. So today is the first class in this series and where we are going to deal with the binary tree. Okay. So, by the way, the prerequisites you can say for this particular series is that I'm expecting that you already know binary trees, okay, and you are little bit familiar about the gate PYQs also, which means you have tried the gate PYQs also. Okay. So let's get started. Now, what is a binary tree? Let me just tell you very quick definition, even if you are seeing it first time, so you will get to understand. Okay. What is a binary tree? So binary tree is basically a tree which is having at most two children, which means it can have one children, zero children, or two children. So suppose if I say this is structure, yes, this is a binary tree. Is this a binary tree? Just along this, yes, this is also a binary tree because this is having zero nodes. Okay, you can have any number of nodes, doesn't matter. Is this a binary tree? Yes, because some of the nodes are having one children, some of the nodes are having two children, like that, right? So these all are the binary trees. Okay. Now, now let's just move to one property of the binary tree. Okay, one property of binary tree. What is that property? It see, by the way, based on this property, there has been many PYQs that has been asked. Okay, first let me write the property. The property of one of the popular property of the binary tree is that, or you can say may not be that popular, but still Gate has asked at least I can say 4 to 5 or even more than 5. Okay, actually I think it might be 5 actually. So 4 to 5 Gate PYQs has been asked based on this simple property, and we will solve those PYQs. Don't worry. So 4 to 5 gate PYQs has been asked based on this property. Okay. So let me tell you the property. The property says that suppose you have any binary tree. Okay. In any binary tree, any word is important here. In any binary tree, you can say the number of leaf nodes and the number of nodes which are having degree 2. There is particular relation. So let me write that relation. So basically, in any binary tree, the number of the hash means number, okay? Number of leaf nodes, leaf nodes are equal to number of degree degree 2 nodes plus 1. Okay, this is the property. Let me just explain you this property. That what does this mean? See, if I tell you this binary tree, okay, can you tell me in this binary tree how many leaf nodes are there? Let's just represent those leaf nodes by L. How many leaf nodes are there? I think two, right? How many degree two nodes are there? So maybe I can represent those nodes are degree two. Okay, so degree two nodes. How many degree two nodes are there? Degree means like these. This is connected to how many you can say a descendant, or how many nodes. So basically it is connected to two. So degree two nodes are one, right? So it is connected to these two. So that is why there is one such node which is having degree two. Okay. So I hope you are getting my point. That what I'm trying to say. See here, in this particular tree, the number of leaf nodes are two, and number of degree two nodes are basically one, right? So basically, do you observe here that L, which is number of leaf nodes are equal to number of degree two nodes plus one, isn't it? Is this okay to everyone? So this property is definitely getting satisfied here, right? Now what about any other tree? Let's just make any other tree. For example, this is another tree. How many degree two nodes are here? Just one, right? Just one. Okay. Or maybe let me just give you another example where you have more than one. For example, this. How many degree two nodes are here? Two degree two nodes, right? Two degree two nodes. So degree two nodes you can write here, which are two. Degree two nodes are two. And how many leaf nodes are here? Leaf nodes. These are three, isn't it? These are three. So aren't leaf nodes equal to degree two nodes plus one? Yes, that is there, right? So basically, in any, you can say in any binary tree, it will be satisfied. I hope that's fine to everyone, right? Okay, great. So now let's just quickly prove it. Okay, so actually this is graph theory, proof, but still I will just give you the sketch of the proof. So how to prove? Okay, so let's just prove it. So basically, the thing that I want to prove is that number of leaf nodes leaf nodes are equal to number of degree 2 nodes plus 1. Okay. Suppose I tell you this is just one tree. Okay. I mean just one node. Can you tell me how many leaf nodes are here? Okay. So this is, let's suppose, tree, and I will just ask you leaf nodes here. Leaf nodes. And can you also tell me how many degree 2 nodes are here? In just just a plain this particular tree, you will say leaf nodes are 1, degree 2 nodes are anyway 0, right? Okay, suppose I add one more branch. Okay, so how many leaf nodes are here? Leaf nodes are again one only, and degree 2 nodes are again 0, right? Okay, suppose I add you one more branch here. Now how many leaf nodes are here? Leaf nodes, you will say, now they have incremented to 2, and now the degree 2 nodes are actually 1, right? Degree 2 nodes are 1. So basically, this is anyway greater than this, right? Plus 1. You can easily observe. Now, if you go further, okay, you can take any tree actually for that matter. Okay, you can take any tree. See, you can take any tree. What is happening here? In this tree, okay, whatever is the leaf nodes and degree 2 nodes are earlier. Okay, so the moment I add any of the leaf, okay, suppose this is having only one child earlier. Okay, the moment I add any of the leaf, at that moment what happens? At the same moment, what's going to happen? See, that number of leaf nodes are getting incremented by 1, right? Leaf nodes has got incremented by 1. Okay, they has got incremented by 1. And degree 2 nodes are also getting incremented by 1, right? So they are both getting increment by 1, right? Degree 2 nodes are also getting increment by 1. See, if leaf nodes are getting increment by 1, then degree 2 nodes are also getting increment by 1. That is why the relationship always holds. If leaf nodes are not getting incremented by 1, for example, if I just take this, okay, just this. So if I add one more node, see, leaf node earlier were 3. Now also they are 3, isn't it? Now also they are 3. Leaf nodes are not changing. If leaf nodes are not changing, then number of degree 2 nodes are also not changing. Okay, this is not a degree 2. The moment you make it degree 2, okay, if degree 2 nodes are increasing, then leaf node is also increasing. So basically, they are increasing by the same amount all the time. So it is plus 1 always. See, if it is satisfied in the base structure, for example, if it is satisfied here, okay, the moment you add this, leaf nodes are not incrementing. Number of degree 2 nodes are also not incrementing. The moment you add this, leaf node got incremented by 1. Number of degree 2 nodes also got incremented by 1, right? The moment you add this, leaf node, degree 2 nodes, both are not incrementing. The moment you add this, now leaf nodes are getting incremented by 1, right? Now it is 3. But degree 2 nodes are also getting incremented by 1. See, this got incremented. See what I'm trying to say? That if you add this, if you just add this, then leaf nodes are not incrementing. Don't think that leaf nodes are incrementing. Why? Because it got internal node, and now the leaf nodes are 2 only. Earlier was also 2. Here also 2, right? But the moment you add this, okay, for example, the moment you add this, leaf node are getting incremented by 1. At the same time, internal node or degree 2 nodes are getting incremented by 1. Okay, I hope that's fine. Now tell me, can I say like this? Can I say like this? That number of leaf nodes, actually it is very important. Okay, I don't know why for such simple theorem they have asked, I think more than 5 times they have asked questions. Okay, so number of leaf nodes equal to number of degree 2 nodes plus 1. Can I say like this? Okay, now tell me, can I say like this? Number of leaf nodes are equal to number of internal nodes plus 1. Can I say this? Just tell me. Number of internal nodes plus 1. See, we cannot say this. See, it is only for the degree 2 nodes, right? It is only for the degree 2 nodes. It is not, okay, it is not for number of internal nodes. Okay, it is not for number of internal nodes. So this is only applicable for the degree 2 nodes. So this is false. So you can say this is false, right? This is true. Okay. So always remember this, because this seems to be easy, but this is actually important. GATE has asked many questions regarding this theorem. Okay. Now assume you have full tree. Okay. Assume we have full tree. What is full tree? Do anyone remember? Assume we have full tree. Full tree means a tree which have either zero, any node has, okay, any node has zero or two children, right? Which means if you have this kind of tree where every node is either having two children, for example, this is having two children, or it is having zero children. So for example, this is a full tree. Okay, this is a full tree. This is a full tree. Why? Because every node is basically having two children. Every internal node is having two children, right? So this is a full tree. Now in full tree, if it is internal node, then it is degree 2 nodes also, right? So basically in full tree, I can say that internal nodes are same as degree 2 nodes. Internal nodes are same as degree 2 nodes. Okay. But this is only applicable for the full tree. Okay. Now you tell me, given a full tree, is this also true? See, let me write this there only. Okay. See, the above line is anyway true for every tree. Okay. But the below line, is this true for the full tree? See, this is an universally true, right? This is universal. Okay. But since the internal nodes and degree 2 nodes are same here, so you can replace these two for the full tree only. Okay. For full tree, this is also true. This is also true. Okay. I hope you understood. So basically, this is what happens in full tree, right? Okay. So now we know one theorem, which is very simple theorem, and I hope you won't be doing any mistake in that theorem, right? Okay. Let me know if there is any doubt in that theorem. So there are actually many questions from that particular theorem. I will be doing the questions little later on, but let me just give you one of the question. This question has been asked in GATE CSE 2015. Okay, all the questions are actually there in the slides, so it will come later. But just for the suspense, like just for revealing the suspense, I'm just telling that let's just solve this question. They are saying there are in in a binary tree. Okay, they are not saying full tree. They are saying in a binary tree there are 20 leaves. Okay, then they're asking degree 2 nodes. Then how many nodes are having degree 2? How many nodes are having degree 2? What do you think? What is the answer? See, leaf nodes are actually one greater than degree 2 nodes, right? Degree 2 plus 1. So degree 2 nodes will be how many? So from here you can easily figure out these will be 19, right? Is this fine to everyone? Okay. Okay, great. Now let's just talk about little bit about the perfect tree. Do you know the perfect tree? What is a perfect tree? A tree which is you can say having all the levels filled, right? So this perfect tree and full tree definitions, I hope you might be knowing. So there is something called full tree. Okay. So this definition you might be knowing. What is that? That any child, or like just to make it very clear, that every child, every node basically, node should have zero or two children, right? And the last one is there is something called as complete tree. What is that complete tree? Complete tree is saying that all levels are full, all levels are filled completely except last level, which is filled left to right. Okay, you might know these definitions, which is filled left to right. Now, actually, these two definitions are standard definitions, which means that everyone are using these two definitions. Okay, so this is a standard definition. This is also a standard definition. But sometimes when they write complete tree, they actually mean to write perfect tree. I mean, these two definitions, I mean, for the complete tree, they actually mean that, okay, all levels are completely filled. Okay. But that's fine. Like, you don't need to be worrying about it. They will give in the question, okay, what they mean by complete tree. But the definition is, you can say author dependent, sometimes author dependent. Okay. But yeah, these two definitions are not having any ambiguity. These two definitions are perfectly, defined everywhere like this only. But for the complete tree, in most of the places it defined like this, but in one or two places which are also standard, it defined like this. Okay, just like perfect tree, they either say perfect tree or complete tree. So anyway, let's not worry about it. Okay, now let's just talk about perfect tree. What is a perfect tree? A tree which is actually perfect, right? Like this. Okay, now there is something called height of the tree. So I will they will define the notation. I will say this is having height, let's suppose 0. This is having height 1. This is having height 2. Okay. So basically, in other words, you can say like the total height is, let's suppose, h. Here the h value is 2. Okay. Now you tell me that how many total nodes are there if height is h. Okay. First you tell me number of leaf nodes. Leaf nodes for height h. I'm talking about perfect tree only. Okay. I'm talking about perfect tree only. See, this is having 2 power 0, 2 power 1. This level is having 2 power 1. Okay, this level is having 2 power 2. And I'm just asking level wise, right? I'm just asking basically 0, 1, 2, and 2 is the height. So basically this is just h. Okay, so I'm just asking at the last level how many nodes you have. It is just 2 power h, isn't it? Just 2 power h. It is very easy. Okay. If I just ask you number of internal nodes in terms of the h, okay, internal nodes, then can you tell in terms of the h? See, number of internal nodes means summation of all these. This is one way to tell. Another way is that you can use the theorem. Okay. Another way is that you can use the theorem. What is that theorem? That number of actually here all the internal nodes are degree 2. It will be one lesser than these, right? It will be one lesser than these. So 2 power h minus 1. Is this fine to everyone? Let me know. Okay. So it is 2 power h minus 1. See, what I'm asking is that how many leaf nodes are here in this perfect tree. Now how many internal nodes are here? Okay, so you can have any tree, any perfect tree basically. Suppose this height is h. Okay, I'm saying this height is h. Okay, this is at height 0. Suppose this is at height 1, like this, right? These are the heights. Okay, so this is at height h. Now if I ask you how many leaf nodes are present, you can say at any level, the number of nodes are 2 power that particular level. So leaf nodes are, okay, leaf nodes are 2 power h, right? Internal nodes are actually all the internal nodes are degree 2 nodes here only, degree 2 nodes, which are one lesser than leaf. Okay, 2 power h minus 1. One other way to find out the internal nodes could be, okay, you can quickly find out by the summation of all these nodes. How? You can just sum it up, right? 2 power 0 plus 2 power 1 plus 2 power 2 like this till 2 power h minus 1. Till height h minus 1 you want to sum it up. So it will be 2 power, if this is let's suppose x, then it is basically generally 2 power h plus 1 minus 1, right? X plus 1. So basically x plus 1 minus 1, if this is x. So which means that actually it will be, you if you calculate it, it will be 2 power h minus 1. Okay. You can easily calculate it. It is 2 power h minus 1. Is this fine to everyone? Okay. So finding out internal nodes could be using the theorem which is just like this, or you can sum it up. Okay. Both ways are fine. Right? Okay. Suppose instead of in terms of the height, instead of if I say in terms of the node, okay, suppose these are the perfect tree only, but I gave you these are the n nodes. So okay, instead of heights, let me talk about the nodes. Let's suppose n. Okay, this is perfect tree. Now, if this is given to you, and suppose if I ask you the same thing, which is number of leaf nodes. Okay, so how many number of leaf nodes will be there? Can you tell me? This is also easy. Okay, if you apply the theorem. If you apply the theorem, this will also be easy. Just think about it. See, the total number of nodes are given to you, which is n, which is leaf plus internal, isn't it? And now you also know that leaf are or the internal you can replace anything. Okay, you can replace L with I plus 1, right? I mean, leaf are just one greater than internal. So from here, you can say that internal nodes are basically n minus 1 by 2. N minus 1 by 2. So number of leaf nodes will be how much? If these many internal nodes are here, 1 greater than that, right? N minus 1 by 2 plus 1, right? So which is basically n plus 1 by 2. Okay. So these many, you can say internal nodes are here. Okay, so finding out internal nodes or the leaf nodes are very easy if this is perfect tree, right? In terms of height also you can do it. In terms of the number of nodes also you can do it, right? Now, what is the relation between height and number of nodes? Okay, you can also find it out very easily. Let me quickly do it, and then we will be solving 8 PYQs. Don't worry. So just few of the things I want to tell. Okay. So relationship between. So this is again a perfect tree. Okay. Suppose n is the number of nodes and h is the height of the tree. Okay. So this is number of nodes, number of nodes. This is height of tree. Okay. So what could be the relationship? This is also very easy. How? See, the total number of nodes are n, which are nothing but 2 power 0 plus 2 power 1 till 2 power h, isn't it? So basically, this is nothing but 2 power h plus 1 minus 1. Right? So from here, you can find out the relationship. I mean, if you want, you can find out the h in terms of the n, or n is already in terms of the n, h will be. So basically, you can say in one box, you can write n equal to 2 power h plus 1 minus 1. Or in another box, you can also write h equal to n plus 1 log of n plus 1 uh, minus 1, right? Something like this. Okay. So is this fine to everyone? Right? Okay. So basically now we know the relationship between these two also. Okay. So let's just do the same exercise for the complete binary tree. So basically, I think now you're comfortable with these things and you will be able to do it, right? I can move to the tree traversals now. So basically, the only thing that we need to do, we need to just count the nodes and these things like this. Or maybe I can do it for the complete binary tree first, and then we can move to the tree traversals, okay, quickly. And then I will move to the gate PYQs. So suppose I have complete binary tree. Complete binary tree looks like this. Okay. Complete binary tree looks like this. Okay. So now suppose in this is the complete binary tree. Okay. Now, suppose if I ask you the things, let's suppose let the height is given to be h. Okay, again, let's suppose the height is h here. Okay. Now, suppose they ask you here, since they cannot ask you the number of nodes directly, they can ask you the minimum number of nodes, or they can ask you the maximum number of nodes. So, can you tell me the both the numbers? Minimum number of nodes and maximum number of nodes. See, maximum will be same as the earlier. Okay. So how many total number of currently I'm asking total number of nodes. So how many total number of nodes will be there? 2 power h plus 1 minus 1. Okay, maximum. Minimum will be instead of h you can put h minus 1. Okay. So 2 power h minus 1. Okay, this is basically till this point, but minimum for the height h, one more should be there. Okay, so plus 1, which is 2 power h, right? Is this fine to everyone? So basically, this is maximum till this point. Till this point, the maximum this, and then one more. Okay, which is basically this one. So you can find in any other way, like whatever way you like. Okay. In complete binary tree, they can ask minimum or maximum only, right? But suppose they ask you the same question. Okay, minimum, maximum. They ask you the same question for a general binary tree. Okay, I mean just a binary tree. They don't say it is complete or anything else. They just say it is a binary tree only. Okay, it could be anything. I mean, need not to be complete. Suppose they say height is h. Okay, so what is the maximum number of nodes for the height h? See, let me tell you minimum. Okay, for the minimum, actually it has to be zigzag, right? Or you can make it skewed if you're more comfortable with the skewed. Okay, so height is 0, 1, 2, 3, like this, right? So if height is 0 here, 1 here, 2 here, 3 here. So for height h, how many nodes minimum could be there? Tell me. See, this height is 3, 0, 1, 2, 3, right? This height is 3. So nodes are, minimum number of nodes will be 4, right? So basically minimum number of nodes could be h plus 1. Okay, if this is h, then minimum number of nodes could be h plus 1. Maximum is same everywhere, which is 2 power h plus 1 minus 1. Okay, because you have to fill all the levels. Maximum is anyway same everywhere. Okay, there is no difference in the maximum. Understood? Okay, so I hope that's fine. Now let's just move to the next thing, which is tree traversals. Tree traversals. Okay, so you might already be knowing there are pre-order, post-order, and in-order. So these are the three type of tree traversals, right? So Nitin is saying that at least interact with the viewer. Yes, yes, I'm already seeing. Okay, I'm already seeing all the comments. So there are like three type of tree traversals. One is pre-order, okay, post-order, and in-order, right? So pre-order means that you are having root first and then left and then right. Post-order means left, right, and root. In-order means left, root, and right. Okay, for left and right I'm just writing L and R. Okay, so you might already be knowing these things. Now let's do one thing. Let's just see some tree and let's just try to make let's just try to draw the traversal of the tree. Okay, suppose I have very simple tree, which is A is here, B, and then C. Let's suppose this is D, E, F, G. Okay, suppose this is the tree that I have, right? Now, suppose I want to know the pre-order here. What could be the pre-order? What could be the in-order? And what could be the post-order? So let's just go one by one. So what is the pre-order? Pre-order means root, left, right. Okay, and this has to be done recursively. Okay, this has to be done recursively. So what is the root here? Root is A. What is left? Left is this whole. So for the left, you actually you can make the space of 3. Okay, and then for the right, so after the right will start. So right is also 3 nodes. Okay. Now do the recursively. Okay. So what is the here? If you come here, then what is the root? Root is B, and then left is C and right. Right. Root left right. Similarly here also root E, left is F, and then right is G. Okay. What is the post order? Or maybe first let me write in order. What is the in order? In order is basically left, root, and right. Okay. So first you do left, right? First you do left part. See, root will be in the between. Okay. And then three things will be on the left and three things will be on the right. Okay. So first you do the left part. So basically on the left, again, you do recursively left first and then root and then right. Here also left first and then root and then right. Okay. Great. Now, what is the post order? For the post order, you write left, right, and root. Okay. For the post order, you write this. So which means left is you can say, see, for the root is A. So here three things will be on the left and then three things will be on the right. Okay. So left is this. Again, you write left, right, and root. And then you write left, right, and root. Okay. So that's how you can write pre-order, post orders, and in order. Okay. I hope you already know these things, right? Okay, great. So I was just revising you, right? So let me know if there is any doubt here. Now, interestingly, you can also do this in order by the projection. Projection in the sense that you can say that, okay, let me project it, okay, directly. Let me skew it and let me project it. So if you do the projection, you will be getting, let me go to the next page and let me tell you the shortcut for the in order. Okay, this is the shortcut for the in order. Actually, it is very useful. You will get to know where in solving the question, it is useful not just to find the in order and all, but to understand the property of something you might already know, which is binary search tree. Okay, binary search tree in order is actually sorted. You will get to know how. See, you just directly squeeze it. Okay, directly project it. If you project it, it will be C, B, D, A, F, E, G. Okay, it will be like this. This is the in order. You don't need to do anything. This is the in order. You can check it. CBD, CBD, AFEG, right? AFEG. So this is the in order that we have. So you can easily find out in order in this way. Okay. So finding in order using the, you can say projection. So in order shortcut. This is in order shortcut using projection. Okay. Is this fine to everyone? Now, let's suppose that some in order and pre-order is given, then can you make a tree? Okay. Suppose some in order is given to you and also pre-order is given to you. Then can you make a unique tree? You might have solved these questions, but I'm just quickly revising so that we can solve the gate PYQs. Okay. So suppose the in order is given like this, which is G, D, H, B, E, I, A, F, J, C. Okay. And pre-order is given like this, A, B, D, G, H, E, I, C, F, J. Right. Now suppose they ask you to make the tree out of these two. So how to do it? Let's just see. Okay, this is going to be a little more challenging. So what's the first step that you need to do? Find where is the using the in order and pre-order. So where is the root? Using the pre-order, you can find out the root. Okay. So pre-order is saying root left right, right? Is this fine to everyone? And what does the in order say? In order say left, right, left, root, right. Okay. So it says in order means left, root, and right. So using the pre-order, can you tell me what is the root? Root is anyway A, right? It is clearly visible. Okay. Root is anyway A. So you can say A is the root. Okay. So this is done. I mean, A is the root. And how to find out the root? Using the pre-order, we found out that root is A. Okay. Because pre-order is saying root is A. Now you just go in the in order and just see what is on the left of this and what is on the right of this. Okay. So if you observe, then on the left there is a too many nodes. So on the left of this is this, and in order is saying on right of this is FJC. On right of this is FJC. Okay. So till now, our, you can say, iteration number one is completed. Okay, where we are basically identifying the root. And once we identify the root, using the pre-order, you are identifying the root, and then you just again go back to in order, because pre-order job will be just to identify the root. Okay, just go back to in order and just to divide this problem into two different problems or two sub problems, you can say. Okay, now you have to do these things recursively. Okay, so now you tell me, okay, if I just ask you, given this, now you tell me what is the root again. So our steps will be same. Step is that first find out the root using the pre-order. Okay, so what is the root among these all? So if you notice GDB, GDH, okay, among all, see B is coming first. Okay, so whatever is coming first is root. So this is root again. Okay, this is on the left and this is on the right. So you can make this is on the left and this on the right. Again, find out the root using the pre-order among these three, GDH. Okay, so first is coming D. So basically D is root again. Okay, and left is this. And using in order, you can check what is on the left and what is on the right. So basically the in order I have already copied. Okay, what I just copied was actually in order. I mean the order is actually in order, so I don't have to again and again look at the in order. Okay, because I copied actually in order here. Okay, so I hope you are getting my point. So these are the two steps. Step one, find out root using pre-order. Step two, separate left right using in order. Separate left right using in order. Okay. So these are the two steps, very easy steps. Okay. Separate left and right using in order. Okay. Now, now we have here, we have this as left. Here also we have found out what is left and right. Here these two are there. Now what is the root among E and I? Root is E because E is coming first. Okay. And automatically I will be on the right. What is among FJC? What is root? C is the root and FJ on the left. So you can say C is the root. Okay. And FJ is on the left. And among FJ, who is the root? F is the root and J is on the right. Okay. So basically it is looking like this. Is this fine to everyone? Okay, great. So this is not too tricky. I think this is okay to everyone, right? Okay. Can you do the same exercise? Let's suppose if the post order is given, yes, the steps will be same. Okay, using the pre-order or the post order, you can find out the root, and then using the in order, you can just separate it out. Okay, what is on the left, what is on the right. Very much simple. Okay. Suppose I give you, let's suppose I give you the pre-order alone. Okay, pre-order alone is given to you. Okay, suppose it is ABC. Now, can you make the tree? See, earlier I was able to find the root here, and then I was able to separate using the in order. Okay. So suppose here the pre-order is given to you, right? Now, can you basically can you tell me what is the root? So basically root left, right. Okay. So what is the root? Can you tell me? Yes, A is the root. That is correct. Now, if you want, you can say that okay, B is on the left, C is on the right, right? So A, B, C, this is the answer. But is this the only answer? This is correct. But is this the only answer? Actually, no. See here that it is also possible that A is the root. There is no denying this, right? That there is nothing on the left. Okay. I mean, this BC on the right only. Okay. No one is saying that BC from BC B has to be on the left like that, right? No. So it could be null. Okay. Null on the left and BC on the right. Now among BC root is B, but you don't know about the C, right? So here among BC, you can say from here you can say there are two possibilities. Okay. So A is there is on the left there is nothing, on the right this B C could be this, A is there, this is this. Actually find pre-order of this, which is root left and right. So left is nothing, right is this, and root left right, you will be getting for these three trees you will be getting the same pre-order. Okay. Similarly you can say on the left this is BC, on the right this is null. Again there are two possibilities in the similar way, okay, which is A, B, C like this, or A, B and C. Okay. Again there are two possibilities. So basically this is 1, 2, 3, 4, 5 trees are there just using this pre-order. So what I'm trying to say that, see, this is one tree, okay, or one pre-order that you have got. Now there are multiple pre-orders possible. What is that? A is there, okay, on the left there is nothing. Okay, you can let me write null just for the sake of simplicity. On the right this could be BC. Okay, now again BC, for the BC there are two ways. Okay, two ways to basically make the C, you can say. So one is you can write the C on the left, or you can write C on the right. For all of these three you will be getting the same pre-order, and the same thing you can do for the left, which means that A is there, on the left BC is there, on the right there is nothing. Okay, so on the right there is null. Now among this BC also, okay, there are two possibilities. So basically you will be writing B anyway, right? Now the C could be on the left or it could be on the right. Okay, so here the C could be on the left or could be on the right. Okay, so these are the 5 different trees are possible. Different trees are possible. Okay. So there is a formula to find out the number of different trees using the given number of nodes. If these are the n nodes, then there's a formula, something called 2n cn divided by n plus 1, something like this. So actually you don't need to remember that formula, but I'm telling you, if this is basically only pre-order is given, then there are multiple possible trees which are having the same pre-order. Okay. There could be multiple possible trees which are having the same pre-order. So someone is saying that this I did not think about. So we need to do both in order. Yes. So basically we need to know both in order and pre-order. Okay. Just knowing the pre-order or just knowing the post-order is not enough. Right. So basically similarly, if you have the post-order, the things will be same. Okay. It won't be basically different. So basically I can say that along with the, so along with the in order, you can say either pre-order or along with the in order, post order is also, or the post order. Okay, either this or this is needed. Can the pre and post both do it? No. Okay, so basically pre order order plus post order? Can both do it? Do it? No. Okay. They can uniquely determine the tree. They can uniquely determine the tree. Okay. Can pre and post both uniquely? No. Okay. Why that is the case? Because actually for the pre and post both also, okay, you can find out the root. I mean, pre and post are basically used to find out the root. Okay, their main job is to find out the root. Now to separate them out, we need in order also. Okay. So you can write like this, that pre and post we use we use pre and post order to identify root, but but to separate left and right we need in order, right? But to separate left and right we need in order. Okay, now let's just see some interesting cases. Okay, so let's just see some interesting case. Suppose uh I say that there is, full tree. Okay, so let me write some interesting case. And let me just tell you that about this interesting case, there is one interesting story about this case. Is that not this year, last year, okay, in GATE 2024, in GATE DA 2024, this was asked. Okay. I will tell you what is that interesting case, but before that, let me tell you the interesting story. In GATE D 2024, this was asked. Also, we have already covered it before GATE D 2024, and we have also uploaded, okay, just on the day of GATE D 2024, when this question was asked, this case was asked, we have also uploaded the video on the YouTube on the same day. From the lectures, we have uploaded video on the YouTube also. Okay, on the same day basically. So also let me tell you one interesting thing. We have already covered this before GATE D 2024, and we are sure that no other coaching had already covered it. No other, any single coaching had already covered, obviously to best of our knowledge. Okay, so whatever we can think of, that no other coaching had already covered this. Okay. Okay, so let me just go about interesting case. So what is that interesting case? See, see, currently we are at the full tree. Oh, sorry, we are in the general tree. So in the general case, this happens, which means you need in order anyway. Okay. Now suppose we talk about the interesting case of full tree. Suppose the tree is full, which means either 0 or 2 children, right? In that case, let me just tell you that even okay, so in this case, even pre plus post order will work. Okay, let me just tell you how. See, consider a full binary tree. Okay, consider a full binary tree. In full binary tree, let's suppose there is a pre-order and let's suppose there is a post-order. Okay, suppose the pre-order is, so I've already written this, A DHL Z, P, C. Okay. And post order is H, L, D, P, C, Z, A. So this is pre-order and this is post-order. Okay. Now also the condition which is given that it is a full binary tree. Okay. Now let's just try to find out if we can, draw the unique binary tree, unique full binary tree. See, can you tell me the root? Yes, root is A, which is very obvious. So root is A. Okay. So here you can write also, this is root, left, right. This is left, right, root. Okay. So root is A. Okay. So both are agreeing on this root is A. Now it must be having two children. See, root is A. Now this, I need to find out which is on the left or now after finding on the root and which is on the right. Can this is on the left, D alone? Yes. Can DH? Yes. Can DHL? Yes. Can DHLZ? Yes. Can DHLP? Yes. DHLZP. But can this all of this can on the left? Can this all of this on the left? Okay, tell me, can this all of this be on the left? No, because if everything is on the left, then what will be on the right? At least one of the child has to be on the right. So basically, I will say that everything cannot be on the left. Okay. Anyway, so basically, I found out that A is the root, and now I need to find out what is the left, what is the right. Okay. So do you want to guess? See, either this is on the left, this is on the left, this is on the left, something like this, right? I mean, it must has to start with D. Okay, must has to start with D. So basically, once you find out the root, okay, now here also you can say using the pre-order, you can say that D is the root. Okay, for the left subtree. I mean, whatever is on the left, you don't know currently, but D must be there. Okay, D must be there. One thing is for sure, D must be there. Okay, and for the left subtree, if you again apply the pre-order, which is root left right, so basically root will be D only. Okay, so root will be D. So for the left subtree, okay, root will be D. Why? Because it must has to start, I mean, D has to be on the left, and 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 you can say that it has to again follow recursively the same structure, which is root left right. So D must be the root only. Okay, root, because root comes first. So now you know the root of the left subtree, right? Now you go to the post order, and in the post order, there is one very interesting thing that you can notice is that the post order end with the root. Okay, see, the pre-order start with the root, so that is why you can say that D must be the root. That is why you told that, okay, D must be the root. Pre-order start with the root. Post order end with the root. Okay, so basically it must be ending, if it is D here, so you can say before D whatever is coming, it must be ending with the root, right? So this whole thing is on the left actually. Okay, so this whole thing, this H and L. Okay, so basically you can say D is the root. Currently I don't know, but D is the root, and I need to also find out the left and right. Okay, so you can say root left right. Okay, so basically here there is no ambiguity that can both of the things can go to the right or can both of the things can go to the left. It is not possible, right? So D is here, and now after D, either using pre-order or using post-order, you know what is the left and right. Okay, so you either using this, you can say that, okay, left, right, and root. So left is H, right is this. So what is the step that we have done? Just see carefully that first we have found out, okay, what is A, right? I mean, what is the root? There was no ambiguity in the finding root. Tell me, will there be then any ambiguity? No, right? Now, after that, you know that, okay, you go to the pre-order. Okay, the next step is to go to the pre-order, and to find out the, left root, you just see that, okay, this has to be on the left. I mean, one of this, okay, either this, or I mean, D must be on the left actually. So you know, okay, this has to be on the left, and since this is a pre-order, so it must start with the root. So left subtree root is D only. Okay. Now go to the post order and see where D is ending, because this is the end. Okay, post order says that, okay, root is the end. Okay, so from here you got to know that this is the thing, right? Now PCZ is remaining only. Okay, so P CZ. Yes, these three are remaining. So among these three on the will be on the right. So Z is root. Okay, Z is root, and left is P, very easily observable, and right is C. Okay, from anything you can say. So basically, if it is not a full tree, if it is not a full tree, then here will not be any confusion. Yes, there will be a confusion that okay, Z is here, maybe PC both on the right, maybe P is here and then C like this, or maybe P is here and C like this. So there will be a confusion. But currently, since at least one of the child will be on the left, at least one of the child in the on the right, this thing is actually making sure that there is no ambiguity anywhere. Okay. Is this clear that how we are making this particular tree? Let me know. Okay. So let's just do one thing. Let's solve one more question. Maybe you will get to understand. Okay. Again, this is a full tree. Okay. So let's again take full binary tree. In case of full binary tree, let's take two things, which is pre-order, and this exact same question has been asked in GATE D 2024. Okay, exact same question, right? Suppose the pre-order is here. Let's suppose A, B, C, D, B, C, D, F, G, E. Okay, suppose this is the pre-order. Suppose the post order is C, F, G, D, B, E, A. First tell me, isn't it easy to find out the root? Yes, right? Tell me the root. Okay. So the root is anyway A. Okay, root is A. So it is very easy to talk about the root. Root is A. Now tell me left subtree root. Immediately tell me. See, here it will be root, right? Left subtree anyway, like B will be the root. See, here A is the root of the whole tree and B is the root of the left subtree. Why? Because on the left, at least one has to be there, right? And B has to be on the left, and it actually, it says that root left, right. This is left, right root, right? So immediately AB, this has to be actually immediate. Okay, there is no confusion till this point. If this is whatever is written here, you just write in the pre-order, you just write like this. Okay, there should not be any confusion till this point, right? Okay. Now you go to the post order and just see where is B. This is B. The whole thing. Okay. This is left, right root. So this whole thing is actually left and right. I need to find out which is left, which is right. But yeah, this whole thing is something. I mean, basically you can say the CFGD will be either on the left or right. Right. Now go to CFDG. This. So C will be again the root of left. Right. C will be again the root of left. So basically C will be like this, right? Let me know if that is fine to everyone. Okay. So once you find out the root, always go to the post order. Okay. See where is this C is ending. So basically C doesn't have anything else. So C is actually a leaf because it ends with the root. Okay. So C doesn't have anything on the left, right? So this is fine. Okay. So basically CDGF. So these things we are talking about, right? Okay. So C is fixed. So basically you got to know that it's okay. C is on the left. And then with this B, like we want to know that what is on the left, what is on the right, right? So this whole thing has to be distributed among left and right. Okay. Then I got to know that okay, C is on the left, definitely. What is basically on the left and right of C? There is nothing, right? So basically everything else, which is DFG, okay, is on the right of B. Okay. So DFG. Now again, here, what is the root? Whatever is the first coming is the root, right? So D is the root, F will be on the left, and G will be on the right. Is this fine to everyone? Now only E is remaining. E you can write here. Okay. See what is happening here. Let me just tell you. You okay. See, you first write these two things. Okay. Basically, the only point I want to convey here is that there is no ambiguity. Okay. See, you first write A, which is the root, and then B, right? Okay. So this is fine. Now you know that okay, A is here, B is here. Now everything here has to be distributed among left and right. Okay. So something on the left, something on the right. Now we need to check that okay, how it is going to distribute it. We go here, C is coming first, which means left. I mean, basically you can say that here, obviously you will be writing the left first, right? So basically C is the root of the left. Okay. And before C there is nothing. Okay. See, wherever is this C, you always see the before that. Okay. The existing see here B was there. So before that everything has to be distributed among left and right. So before C there is nothing. So there is nothing to distribute. You just got this F, G and D. So this is D, G, F here. So root will be D because D is coming first, and F and G. And E is the only thing which is remaining. So you can write E here. Okay. So actually there will not be any confusion. In case of full binary tree, if you have pre and post order, then there is no confusion. So you can say in general binary tree, for any binary tree, in order is needed, right? In order plus either pre or in order plus post. These two things will be there, but pre plus post won't work for any general, right? Okay. But if it is full binary tree, okay, if it is full binary tree, so you can say for full binary tree, everything works. So any of these two combination work. Okay. Any of these two combination work. Is this fine to everyone? So actually it has been asked in gate DA. Let me just tell you. Maybe I will be having the slides. Yes. So this is the question which they have asked in gate DA. They are saying, recently they've asked in GREE 2024, they are saying, consider the following three traversals on the full binary tree. Okay. So these three traversals are giving, but they are saying full binary tree. Actually, this particular word was missed by almost, every student. And yes, there are like many students who made it correct, and those were actually Go classes students only. So most of the students missed it, even though they do not miss it, actually they did not know the concept. So even though they have noticed it, but they were not able to make it correct. They were thinking that in order is needed. But actually this was MSQ. Either this, any two works. Okay. Single doesn't work. So most student miss this. Right? Single doesn't work. Is this fine to everyone? Let me know. Okay. Now, let me tell you one more interesting case, okay, which is for the complete binary tree. So this is one more which has not been asked in gate till now, but they may ask it anytime. One more interesting case. Okay. This is a case of complete binary. And all of these cases we have already told. In our lectures, they were already present before gate D 2024. Okay, they were already there. Right. So yes, we will share the annotated notes of these lectures. Okay, don't worry, we will share the annotated notes also. So one more interesting case of complete binary tree. Okay. Suppose there is a complete binary tree. Maybe you can have something like this. Or let me just give you some pre-order is given for the complete binary tree. Let me tell you that using just one of the order, it could be any order, you can very easily make the complete binary tree just using one of the order. Okay, it is actually very easy. There is no confusion here because only one order is given, and the procedure is also very simple. Okay, suppose this is the pre-order that you have 1954. It could be anything, doesn't matter. Some random numbers I'm writing. Okay, 87. Suppose this is the pre-order and I want to check if I can make the complete binary tree or not. Okay, you just check how many nodes are there. 1, 2, 3, 4, 5, 6, 7, 8, right? 3, 6, 7, 8. Yes. Okay, so let's just do one thing. Here, let me make a complete binary tree with the 8 nodes. 3, 4, 5, 6, 7, 8, right? This is the complete binary tree with the 8 nodes. Now what you need to do? You just need to write the pre-order of this tree. Tell me the pre-order of this tree. Okay, very simple procedure. Pre-order means root, left, and right. What is the root here? A is the root. Okay, on the left, this whole thing is there. So basically, four things, right? So 1, 2, 3, 4. On the right, there will be 3 things. Okay. Now, again, root will be there, which is B, right? And then left and right. So left and right. So right will be E. So root will be there, which is D, and then left. Okay. Again, root, left, and right. Okay. So this is the pre-order that you have. So let me write the pre-order here. What is the pre-order that you have got? Pre-order that we have got is actually A, A, B, D, H, E, C, F, G. Okay. See, for the complete binary tree, this is the only possible structure that we have, isn't it? Now, instead of A, you just write 1. Instead of B, you just write 9. So basically, instead of A, so basically it is just 1-to-1 mapping. That's all. Okay. Now your job is done. Which means instead of A, okay, you just write 1 here. Here instead of B, 9. Instead of C, 6. Okay. Instead of D, 5. Instead of H, 4. Instead of E, 2. Instead of F, 8. Instead of G, 7. Okay, so this tree is having the this particular pre-order which was given to me. So actually for the complete binary tree, since the structure is fixed, okay, so basically they are not giving one extra order, which I completely agree, but they are giving the structure. If the structure is also given to me, okay, if the structure is also given to me, see, this is not only true for the particular complete binary tree or tree. Basically, if they give me a structure, okay, some skeleton is given to me. Let's suppose they say this is the skeleton. Okay, this is the skeleton, and the pre-order is, let's suppose 1, 3 here, 1, 3, 4, 5, 6. Okay, these are the 6. 1, 3, 5, 2, 4, 6. Suppose they say this is the pre-order or post order, whatever, right? This is the pre-order is given to me. Plus skeleton is also given to me. Okay, 2 things are given to me here. Then can I not directly fill it? It's easy to fill, right? I just need to fill it. So if skeleton and one of the structure is given, then also I can say only sorry, skeleton and one of the order is given, then only one order is needed. Okay, is this fine to everyone? See what I'm saying. From here you can easily populate the tree or skeleton, right? Is this okay to everyone? So basically in complete binary tree, since skeleton is fixed, So that is why any one of the order is also working. So just to summarize, okay, just to summarize, I can write like this. This is the summary table. So where I can say that, see, that in general binary tree, in order is needed. Okay, in order plus pre-order, or in order plus post-order. So basically either in order plus pre-order or in order plus post-order. Okay. In full binary tree, same as general, which means in order plus pre-order, in order plus post, this will also work, and also pre-order plus post-order also work. Okay, any two will work. And here in complete, any one will work. Any single traversal is enough in order, pre-order, post-order. Okay, is this okay? See, they used to ask this since long time. They means gate. Okay, gate used to ask this since long time. Gate only one time recently asked this, only one time in gate 2024 they asked this. Okay, now my guess is that in future, I don't know, maybe this year. Okay, if your luck is good, then maybe this year. If your luck is not so good, then maybe in coming 2 3 years. But most probably they may ask this in the near future. Okay, so nobody knows when they will be asking, but yes, I can say this could be asked in near future. So is this okay to everyone? That what I'm trying to say, right? So basically, for full tree, you can say any two. Okay, for full tree, any two will work. For complete tree, any one will work. For general binary tree, in order is must, and if along with the in order, pre-order or post. Okay, I hope that is fine to everyone. Okay. Okay. So basically, one thing I got to know, that if skeleton is given to you, then any order is fine, right? Then in that case, any order, any tree traversal order, basically, you can say. Okay. Skeleton plus any tree traversal order will fine. So it will uniquely determine tree. Yes, this is the first class in the series. Okay, this is the first class. Understood? Okay. Now let's just solve a few questions quickly. Okay. Suppose they say state whether the following statement is true or false. It is possible to construct a binary tree uniquely using pre-order and post-order traversals are given. This question has been asked in GATE CSE 1987. Tell me quickly. Okay. Because this is easy question, so just tell me quickly. So answer is true or false. It is, you can say, false, right? Okay. Using pre and post, it is false. So they are saying construct a binary tree whose pre-order traversal is this and in-order traversal is, okay, sorry, I think I forgot to copy in-order traversal, but yes, this is basically this. Okay, so in-order traversal is this and pre-order traversal is also given. So can you construct? I think this is easy question. You should be able to do it. Can I skip this question? Okay. So basically, let me quickly do it in just 1 second. So in order means left, root, right. Here pre-order means root, left, right. Okay. So k is the root, that is for sure. And then once you determine k, so nl, right? Among nl, you need to determine what is on the left and what is on the right, right? So NL. So basically K is the root and NL is on the left, and remaining thing which is PRMSQT on the right. Okay. So let me just actually go to the next page. So basically this is here, and you can keep on doing it. Okay. So you can keep on doing it, and you can find out what is the tree. Okay. Since there are many questions, I'm skipping this question. I hope you do it as an homework. Okay. This is easy question only. Let's see this question. This has been asked in 1991. So what they are saying, if binary tree in the figure is traverse in this tra traverse in order, then the order in which the nodes will be visited. Basically, they're asking for the in order traversal. Okay, they're asking for the in order traversal, which means they're asking for the left, root, and right. Okay, that's very easy. Left, on the left, basically you can say root is 7. On the left, there will be three things. So here also left, 4, root, and right. Okay. On the right, basically this. So here also left is nothing, and then root. Okay. On the right, this whole thing is there. Then here also left, root, and right. Okay. So 4, 1, 6, 7, 3, 2, 5, 8. 4, 1, 6, 7, 3, 2, 5, 8. Okay. This is the answer. Now let's just go to the next page. So by the way, for the in order, we don't have to do all of this. We can always do the projection. Okay. Projection means you don't, overlap like this. I mean, you don't make 6 here. Okay. And don't project like this. So basically, if this is on the left of 7, then always draw on the left of 7 only. Okay. Don't draw 6 like this and then say, okay, this is the projection. No. Projection means like draw on the left of 7 only. Okay. If this is on the left side. So just project it. Okay. So basically it will be 4, 1, 6, 7, 3, 2, 5, 8. Okay. So that's how also you can easily do it in order. Okay. So let's just see this question. What they're saying, prove by principle of mathematical induction that for any binary tree in which every non-leaf has two descendants. So basically degree 2 nodes. Basically they are saying degree 2 nodes. And the number of leads is one more than the number of non-leaf nodes. Okay. So basically they are saying if it is a in which every non-leaf nodes are degree 2 nodes. So they are saying that if it is a full tree, okay. So basically they're just asking us to prove leaf nodes are equal to degree 2 nodes plus 1. Okay. By the way, this is a graph theory proof, so I will not go to the proof, but rough sketch we have already seen. Okay. So I can say we have seen this. A proof also we have seen this. A rough proof I can say. So we have seen. It is a graph theory proof, and Deepak sir has done it in the graph theory. I'm sure he must have done it in very good detail. Okay. I know he has done it, but and I'm also sure that he has done it in very good detail. Okay, this is we have. So I mean, this is a graph theory proof, so I'm just skipping it for now. But yeah, rough proof we have already seen. Anyway, now the gate doesn't ask the proof and all. You must be knowing this result. Okay, this is very important to know. Okay, if there are n leaf nodes and degree 2 nodes, so you know it is n minus 1. Okay, this is very easy question, right? Once you know this, that particular simple theorem, then there are many questions that you can easily solve. Okay, so this is n minus 1. Answer is B here. What is the number of binary trees with 3 nodes when we traverse in post order given the sequence ABC? So basically they are saying that post order is given to you. Okay, post order is given to you, which is ABC. How many trees you can make? So I think we have seen we were able to make 5 trees, right? So ABC, this is one tree. Okay, so this is basically left, right, and root, right? So sorry, C will be on the root. C will be on the root, and A could be on the left, and B could be on the right. Okay, C will be on the root, and this whole thing could also be on the left. Okay, this AB could also be on the left, and here also basically B will be the root. Okay, B will be the root, and then two possibilities, right? B will be the root, and then two possibilities. Either A is here or A is here. Similarly, C is here, and then you can say this whole thing, instead of on the left, this whole thing is on the right. So this AB whole thing was on the right. Okay. And then root will be B only. Okay. So B is the root here on the left, right. Okay. So basically there are two possibilities here, two possibilities here, one possibility here. So total five. Okay. Total five. Understood. Which of the following sequence denote the post order? You can find out the post order here. Okay. So basically, from the options also probably you can do it. See, A is the root. So this is anyway not the option. B is not the option. Okay. And then basically it is left, right root. And EF, okay, should be on the right. So basically EF should be the conjugative. Okay. I mean, here EF should be there. So only option C is having EF. Okay. Before A, only option C is having EF. So basically you can say option C is correct. Okay. Because right is EF. I mean, in some order, let's not worry about it. But yes, EF should be there. Okay. EF should be there. A should be there, and before A, EF should be there. Only option C is having that. Okay. Let's see this question. Draw the binary tree where in order and post order is given to you. I think you can do it. Or I think most probably almost same question we have done it. Okay. So in order and post order is given, you can do it like this. Yeah, let's see this question. This is a bit interesting question. So what they're saying that let last post, last and last pre denote the last vertices visited in pre-order, in post-order, in order, and pre-order, respectively, in a complete binary tree. Okay. So there's a complete binary tree. And then they are saying that last post, last and last pre are the three things which are last vertex in the uh, post order, in order, and pre-order. Then which of the following is always true? See, let me just explain the question first. Suppose this is the complete binary tree. Okay. If you write the in order here, or maybe let me write the post first, post, in, and pre. Can you do it quickly? So post means left, right, and root. Okay. So what is the left? So basically root will be on the end. So BCA. In means BAC. Pre means root, left, and right. Okay. So this is last post value. Last post is A, last in is C, and last pre is C. Okay. Last pre is also C in this case. Now they are saying that which of the following is true? Can you tell me? See, it seems like last in and last pre are same, right? It seems like last in and last pre are same. Okay, see, post is not same. Last post is not same. So A and C are not correct. Maybe B is correct. Okay, maybe B is correct. But can we produce a counter example here? See, B is saying last in and last pre. Okay, okay. So I hope you are getting my point here. That see, see. I just need to check. See, we have already disqualified. We have already disqualified two options here, which is A is not correct, right? Because post is basically not equal to anything, right? Maybe pre and last pre and last in are equal. So what is the post basically? Sorry, what is the in? In is left, root, and right. What is the pre? Pre is root, left, and right. Okay. Yeah, we just need to check if I can do something here where basically in and pre last are not same. See, let me just have some bigger binary tree. Okay, which is complete also. See, they are competing for the right? I mean, if for the both of these structure, which is in and pre, both of these structure, whatever is this left root actually doesn't matter. I'm more interested in the last. Okay, I'm more interested in the last, which means, I mean, to make it complete, I can call it X and Y. I mean, actually it doesn't matter. Okay, I'm more interested in the last only. Okay, I'm more interested in the last. Suppose in the last it has only one children, which is D. Okay. So basically it will be left. You need to write left. Okay, let's not worry about it. Left, whatever it is, b, x, y, whatever is the order. Okay, and then root. And then I'm more interested in the right. On the right, I have C and D, right? Here also, in this left and then root. Okay. Again, I'm not interested in the left part. So root is A. Anyway, the left is whatever it is, right? It is basically B, X, Y in whatever order it is. I'm not more interested. On the right side, it is CD. Okay. So here it says root first, root, and then left. Okay. Root and then left. So you notice here that this is C and this is D. These two are also not equal. These two are also not equal, isn't it? See, but this small tree, it seems like that these two are equal, but I just took the next level tree, okay? Because see, I was more interested. See, there is no point in just taking this tree. Was any point in taking this tree? So actually for this just one or two node, it won't matter because see, for these kind of tree, it won't matter because I'm more interested in the last portion. So A left, whatever I'm taking here, it won't be impacting because on the last it will be C. I have to take at least till this point. At least till this point I have to take. Okay, if I'm taking till this point, because see here if I just take x, y, doesn't matter because C will dominate. Okay, C is on the on the last. So I have to take till this point, and then with this counter example you can say that here it is C and here it is D. So that is why this is also not matching. Okay, this is also not matching. Yes, you have to take the intuition here. Okay, everything you cannot know pre-hand. Okay, you have to take the intuition here that okay, for this small example, maybe this is true. Okay, let's just take the bigger example. Okay, for the bigger example, also just need to make sure that where it might conflict, it will be conflict on the right side only. Okay, so left side, whatever you do, doesn't matter. That's why I was not much interested. I have written LL. Okay, on the right, it might be conflicting. Okay, you have to take the example and see if it is working or not. Understood? So basically here, D is the correct answer. For this particular question, D is the correct answer. Now let's see this. Consider label sequence obtained by the following pairs of traversal labeled binary tree, which are the find tree uniquely. Pre, post, in order, post, pre-order, in order. Actually, label order and also post order. I think this will also work or not? No, actually, in order is needed. So, sorry, pre and post won't work. So B is the answer, right? 2 and 3. So you can say B is the answer. This is easy question again. Okay, in order is actually needed. Okay, in order is anyway needed. So in order and label order will also do. Okay. Now let's see this question, what they are saying. So a scheme is storing a binary tree in an array of x as follows. Indexing of x starts x as one at 1 instead of 0, which is fine. So they are saying that you have a binary tree and indexing is starting at 1. So root is stored at x1. Actually, it won't matter. You can start the indexing at 0 and later on you can just do +1 in your answer. Okay, whatever answer you are getting, you can do +1. If you're comfortable with the 0, then you can start with the 0. No, don't worry about the indexing at 1. For a node stored at xi, the left child is, if any, is stored at x of 2i and right child, if any, is stored at x of 2i plus 1. And not able to store any tree, to be able to store any tree of n vertices, the minimum size required of x will be. So they are saying you have any tree. Okay, you can have any tree. For example, this. Okay, suppose this is one. This is one. This is two, or maybe A B C D. Let me write A B C D. This is A. This is B. This is C. This is D. So they are saying you take an array. Okay, you take an array where A is stored. Okay, for example, A is stored at the first place, which is at position 1. If it is position 1, its left will be stored in, you will store at double of it, and right will be you stored at 2i plus 1. Okay, double plus 1. Okay, and its left will be stored at 6. So basically 1, 2, 3, 4, 5, 6. So this is the index 1, this is index 2, this is index 3, this is index 4, this is index 5, this is index 6. So at 2 you will be storing B. That's what they are saying. Okay. At 3 you will be storing C. At 6 you cannot store 4. Okay. At 4 you cannot store D. At 6 only you can store D. Okay. So basically minimum size of the array is required here is of size 6. You're getting my point? So basically here will be null. And at these two positions, because it doesn't have anything, so 4 and 5 is basically empty. So minimum size required here is 6. So basically they are saying for what could be the worst case where you will be needing the maximum size of the array. Okay, that is the question that they are asking. What could be the worst case? So see here, let me just tell you. Suppose you have these three cases. I've written these three cases. Okay. Suppose you have these three cases where you have left tree, I mean left is skewed. If you have left is skewed, then index is, this will be stored at index 1. This is at 2 and this is at 4, this is at 8. So you will be needing the maximum index, you will be needing 8. Okay, till 8 it is fine. But if it is right skewed, it will be stored at index 1, then it will be stored at 3, then it is 7, and then this is 15 basically. Okay. So if it is right skewed, then this will be stored at index 1. This is at 3, this is at 7, this is at index 15. I hope you are understanding. So you need the array of size 15. Suppose this is zigzag. Okay, suppose this is zigzag or any other structure, doesn't matter actually. So see, the maximum you will be needing in the right, because it is 2i plus 1. Okay, this plus 1 is extra and then multiplied by 2 plus 1 again. So basically, if you even have any other zigzag or not, it need not to be zigzag actually. It could be any other tree. Okay, suppose something like this. Okay, so for any other structure, it won't be more than 15. See here you will be storing here 1, and then since it is left, so 2. Since it is right, so 2 into 2 4, and then 5, and then 10. So maximum index needed here also 10. Okay, so here also 10, and in this case it is just 4, right? 1 2 3 and then 4. In this case the index needed is 4 only. But if it is right skewed, it is very much obvious, since it is 2i plus 1 for the right. So if it is right skewed, it will be taking the maximum index or maximum size of array. Okay, so basically they are asking that to build binary on n vertices. If you have n vertices, then what should be the size of x? So basically, what should be the size of x? You can say that for the n, see here, this is 1, this is 2 power I plus 1 like this, or 2i plus 1, and then again 2i plus 1. Okay, you will keep on doing it. Okay, with the example actually you can easily see that if n is 4, then you will be getting 15, right? So D is the correct answer here. Okay, so you can see here that right skewed tree will force extend to the furthest. In general, left skewed will be keep on doubling like this. Right skewed will double like this. Therefore, right skewed will give the maximum index. Okay, so 15 is the correct answer, or in terms of the generalization, 2 power n minus 1. Is this okay to everyone? Okay, great. Okay. So now let's just see this question, what they are saying. In order and pre-order is given to you. Post order they are asking. So first you need to make the tree and then you can find out the post order also. Okay. So this is also easy question, so I'm skipping it. In order and pre-order are given and post order they are asking. Okay, you can do it. Let's see this question. In a binary tree with n nodes, every node has odd number of descendant. Okay. Every node is considered to be its own descendant. Descendant means that every other children. So for example, if this is the case, then descendant of B are all of this. Okay. In this case, they are saying that every node is considered to be its own descendant also. So basically, these are the descendants of B. So generally it is like they generally we don't consider including that also. So they are saying including that number of descendants should be odd. So in actual like number of descendants should be, you can say, even. Okay. So what is the number of nodes in a tree that exactly one child that have exactly one child? So they are saying that every descendant, okay, let's just read it like this: every descendant has even sorry every node has even number of descendant. So which means if this node has to have even number of descendant, then this is BC like this, right? Even number of descendant, I mean it has to have two, or if it is just having one, suppose it is just having one. Now now how many descendant? Currently one. Okay. Now see we have to make the for this A, we have to make the total number of descendants should be even, but currently it is just one. Okay. So A is satisfied, A is having total number of descendants as 2, but B is not having as 2. So the moment you satisfy for B, A is basically imbalancing, A, or A is basically having the odd number of descendants. So basically what I mean to say, that they are asking number of nodes that are having exactly one child. See, the moment you have exactly one child, you will be having, okay, you will be having odd number of descendant, or in other words, if you have to have even number of descendant, okay, even number of descendant of A, then you have to have actually either children of A. See, if I just ask you, suppose the condition is that I have to have even number of descendants of A. Okay. Which means let's suppose I write B and C. Okay. Let's suppose I ask you to have even number of descendants of B. Then either you can stop here. Okay. Or you can say, if I want to have even number of descendants, then at either zero child or two children. Okay. Then only even is possible. If you have just one, then later on you cannot balance it, because you have to balance with the even only. Because see, for this even has to be there, right? Are you getting my point? See, for every node, even has to be there. I mean, number of descendant below it should be even. So for this also even has to be there. So below this has to be even only, right? So even, even, and below B also has to be even only. So basically, if this is, let's suppose, 2, right? Can below B also be the even? Are you getting my point? The point here is that if you just have one child, okay, then here also, since it has to be satisfied recursively, here also you have even number of descendants. Okay. So how many B have? Total we have odd, right? Total we have odd, because one is this, but B want even number of descendant of B. Okay. So basically you can say that if you have only one child, then you cannot have even number of descendant. So either you have to have zero child. For example, if this is the B, either you have to have zero child or you have to have two children. If you have two children, then it is fine. See, even number of descendant till two children, right? And here also, if they expand further, then also even here, they extend further. Doesn't you don't have to worry, because they will take care of themselves. Okay, even, and then these two are even, so total even. I mean, even plus these two. Are you getting my point? So basically, if you have to have even number of descendant, in that case you cannot have any node which is having exactly one child. Okay. So for example, here, if any node try to have exactly one child, okay, exactly one child, and then if you want even number of descendant, okay, then since this will be having even only, okay, because it has to be satisfied, right? This will be having even number of descendant. Now how many descendant B have? Tell me. Odd descendant, right? So basically you cannot have exactly one child. Okay. So either zero or you have to have two. Okay. So basically for this number of Nodes which will be having exactly one child is actually zero only. Okay. So don't worry about it. They are saying including itself. Okay, including every node is considered to be its own descendant. So basically, they are saying odd, but you can read it as even. I mean, because if you just remove this line, okay, you can just read it as even for the sake of simplicity. So if you want even number of descendant, then you cannot have exactly one child. Okay, so that's why it is zero. Because the moment you have exactly one child, since everything will be having even, okay, I have to have even here, then B cannot have, ultimately B cannot have even number of descendant. It will be automatically be odd. Okay. Okay. By the way, this question is related to binary search tree, but let's just try to solve this. What they're saying, we are given a set of n distinct elements and an unlabeled binary tree with n nodes. And how many ways can we populate a tree with a given set so that it becomes a binary search tree? So they are saying they have given the structure unlabeled binary tree, which means structure is given to you. This is important here. Okay, the skeleton is given. If a skeleton is given, and they are saying binary search tree, which means the in order is sorted. So basically in order is also given, one of the order is given, because you can anyway sort it, you can anyway sort these elements, right? And then you can find out the in order. So skeleton is given, and one of the order is given. Can you find out uniquely, or there will be more than one? Will there be more than one tree? Tell me. No, right? There won't be more than one. So basically, if skeleton is given and one of the, okay, traversal is given. So any one of traversal, any one of traversal. Understood? So in that case, there will be only single, okay, single binary tree. Okay. So here B is the answer. This is a good question. Okay. Actually, we will do it more analysis in binary search tree. Okay. See, if the skeleton is given, so it could be any skeleton. Since the in order is fixed, okay, and it is a projection. So basically you sort the numbers and you can just plug in, you can write whatever the numbers, let's suppose 1 2 3 4 5 6 7, and this skeleton is given, and someone asked me how to fill this skeleton with this such that the tree is binary search tree. You can first sort these numbers and then you can just project it, because in order is anyway the projection, and in order is also sorted. Anyway, we will do this more analysis in the binary search tree, but currently I wanted to tell you, if a skeleton is given and any structure is given, okay, indirectly they have asked it. See, directly they have not, indirectly they have said that, okay, binary search tree, but directly they have not asked till now in this form. Like they have not asked that a skeleton is given and unlabeled binary tree is given, and let's suppose pre-order is also given. Okay, this kind of combination they have not asked. Maybe they can ask. Okay, they can ask anytime. Okay. Let's solve this question. What they are saying. Consider a rooted n node binary tree represented using pointers. The best upper bound in the time required to determine the number of subtrees having exactly 4 nodes is. So some binary tree, n node binary tree is given to you, and they are saying number of subtree having exactly 4 nodes. Okay. How much time it will take? See here, that what you can do, you can simply write a code, something like this. So for example, you can have a recursive code which will say, okay, count subtree or some function. Okay, you can go to the left, you can go to the right, and assume that it is basically counting. Okay, counting correctly, which means that left size is size of the left subtree, this is size of right subtree, and size of this particular will be +1. If the size is 4, you can print it. It is just like, okay, just like the in order, pre-order kind of traversal. Okay, just like that kind of recursion, isn't it? So basically, you can say that every node is getting visited Only once. So what is the time this code will be taking? This will be taking order of n only. Okay, order of n. So basically, A will be 1, B will be 0. Okay. So 1 is the correct answer here. Are you getting my point? So this is a very good question. Here they are asking that subtree having exactly 4 nodes or whatever, right? So basically you can instead of 4 they may ask 10 or anything. You can just write that particular 5 if they ask 10 they ask. So basically you can write the code easily. Once you write the code, you will get to understand that you have to go on the left and the right recursively, and you have to. This code is looking exactly same as the tree traversal, right? In tree traversals also we go to the left, right, and root right, and root anyway we print it, and then we go to left, right, something like this. This is same as the tree traversals. Okay, tree traversals also take order of n. This will also take order of n. Okay. Okay. So let's solve this question. What they're saying, the height of a tree uh, is the length of the longest root to leaf in a path. The maximum and minimum number of nodes in a binary tree of height 5. So they are saying length of the longest root to leaf. So basically this height is 1 because this length is 1. Okay. So this height you can say is 1. Okay. You can say this is h equal to 0. This is h equal to 1. If height is 5, then what is the maximum and what is the minimum number of nodes? See, if height is 1, then minimum could be 2. Okay, so it will be 1 more. So 6 will be here. And maximum will be basically 2 power h plus 1, something like this, right? Minus 1. So if you do like h plus 1 minus 1, so it will be 63. Okay, so 63 and 6 should be the answer. Okay, is this okay, everyone? So 2 power h plus 1 minus 1, it would be maximum. We have done these kind of things, right? So, like if you are attending the lecture late, then in the starting we have done this minimum number of nodes, maximum number of nodes kind of thing. A binary tree T has 20 leaves. The number of nodes in T having 2 children. So having 2 children means degree 2 nodes they are asking. It will be, can you tell me quickly? Degree 2 nodes. It will be just 19, one lesser than the leaf nodes, right? One lesser than the leaf nodes. It will be 19. So actually this particular theorem, I don't know how many times they have asked, but they have asked it many times. See again, similar kind of question. Consider a binary tree that has 200 leaf nodes. Then the number of nodes in the tree that have exactly 2 children. Similar kind of question. 199, isn't it? So this is again very easy question. 199. You don't have to do all of this analysis. Okay, you can directly say 199. They've asked this many times. Now let's solve this. Post order is given. The n order is also given. The height of the tree and the length of the longest source of root to the tree. The height of the binary tree above which. So you can solve this, right? I mean, the post order and n order is given. So you can just draw and you can tell the height. Okay. So this is 1, 2, 3, 4. Height is basically they are saying length of the path, longest path. So basically it is 4. Okay. So using this post order and using the n order, you can draw the tree and you can find out the length. Sorry, height of the tree. Okay, let's solve this. Let T be the full binary tree. Okay, so currently they are having full binary tree with 8 leaves. Suppose 2 leaves A and B of T are uniformly and independently at random. The expected value of the distance between A and B in T. Okay, so we will do it a little later. Let me first do some easy questions because it will be quite tough question, or probably we will do it later on. Okay, maybe tomorrow we will be doing it because it will be too tough for today. Okay, or I can keep it in tomorrow also. I can keep it as optional. Okay, this is BFS, DFS kind of question. Just a second. Yeah, let's do this. This has been asked very recently. What they are saying. Consider a binary tree T in which every node has either 0 or 2 children. So basically they are saying full tree, right? Which one of the following is the number of nodes in T that have exactly 2 children? You know the number of nodes, which one of the following is the number of nodes in T? So they are saying n with the number of nodes. N is the total nodes. So the total nodes are given. See, total nodes are n, which are basically leaf plus internal. But interestingly, internal here in the full, okay, in the full binary tree, internal here are the internal nothing but degree 2, right? Degree 2. And I also know that degree 2 are nothing but leaf minus 1. So you can say, or maybe leaf are nothing but degree 2 plus 1. So this is degree 2 plus 1 plus degree 2. This is n. So this is n minus 1 by 2. So B is the answer. Okay, B is the answer. N minus 1 by 2. This is easy. See, using this theorem, they have asked many questions. Recently, okay, very recent, they have asked this question. See, last year only they have asked this question. Okay, so maybe more than 5 times they have asked using this theorem. So that's why this is one of the favorite theorem for the gate. Okay. So what they are saying, let's just read it out. The following three are known to be pre-order, in order and post-order sequence in a binary tree. Following three are known to be pre-post and pre-in order and post-order. But it is not known which is which. Okay. See, you know one thing that in pre, post, and in. Here it is basically, let me write using this. It is root, left, right. This is left, right, root. And this is left, root, and right. See, in pre and post, if like pre start with the root and post end with the root, right? So there has to be, something pre, something post. You can very easily identify. See, for example, if it is starting with the M, anything ending with the M, no. For example, it's starting with the K, anything ending with the K, yes. So basically, using these two, you can say this is ending with the K, so this is pre, and this is, sorry, this is, yeah, ending with the K, so this is post, and this is pre, and K is the root, and no other letter is basically having the same property, which means ending and starting. So is there any other letter which is basically having ending of some sequence and starting of some sequence? No, right? So basically you can say that this is post, this is pre, remaining is in, right? So 1 and 2 are the pre-order, 1 and 2 are the pre-order and in order. No, 1 and 2 are the post and pre, 1 and 2 are the post and pre, 1 and third are pre-order. Second is in order, but nothing more. No. Second and third are the pre-order and in order respect. Yes. So D is the correct answer. Okay. This is also easy question. See, this question we have already done. This was, nice question, and because of the full binary tree, most students miss this. Okay. So here we have already told you that these three are the correct answers. Let's solve this question. What they are saying. Let HILN represent height, number of internal nodes, number of leaf nodes, and total number of nodes respectively in rooted binary tree. Okay, which of the following statement is or are always true? So you can take a simple example. Do I have the answer? Okay, answer I have not written, but yeah, you can take the simple example. For example, okay, what is the height here? 2 is the height, so H is 2, and internal number of nodes. Internal nodes are basically 1, 2, so I is also 2. L with the number of leaf nodes. L is 3. and total number of nodes n. What is the total number of nodes? 1, 2, 3, 4, 5, right? Okay. And then you can check which of this is basically satisfied. Okay. For these kind of questions, you can very easily do using the using some example tree. Okay. So let's just check option A. Is this always true? L is less than or equal to I plus 1. L is less than or equal to I plus 1. For this, it seems to be true. So maybe A is true. Okay. First, we will see which of this we can say it is false. Okay. H plus 1, which is basically 3, less than or equal to N, which is 5, less than or equal to 2 power 3, which is 8 and 7. Yes, for this also, this seems to be true. Okay, currently I'm not saying this is 100% true, but I'm just saying if I can, using just simple example, if I can nullify some of this, okay. H is 2, less than or equal to, I is also 2, less than or equal to 2 power 2, which is 4 minus 1, 3. Okay, this also seems to be true. H is less than or equal to L, okay. H is less than or equal to 3, is less than or equal to 2 power H minus 1. No, so this is false. So D is anyway false. So D we have seen this is false. Okay, because H is here 2 and L is 3, which is okay, but less than or equal to 2 power H minus 1, which is just 2. 3 is not less than or equal to 2. So that is why D is false. But let's just see if all other options are true or false. Okay, so so let me just remove the counter example. So basically, one thing is for sure that D is false. Okay. So can you tell me what is the answer? Is the number of leaf nodes always less than or equal to I plus 1? Just try it. Let me know. So this is MSQ question because they are saying is or are always true. Okay. So let's just see it. Let me also see your response. Okay. So most of you are saying that okay, ABC are true. Let's just check it. Okay. So they are saying leaf number of nodes will be always less than or equal to internal number of nodes plus 1. So let's just check it. Okay. So see, we have seen this that the moment whatever is the see for any tree, the moment you have internal nodes. So currently, let me write the leaf and internal here. Okay. Currently, leaf and internal both are basically you can say 1 and 1 because I mean you can say this is also internal, doesn't matter. Okay. Both both are 1 and 1. Now you increase the leaf by 1. Okay, which is okay. So basically it is a base tree. Now see the moment you increase the leaf also by 1. Okay, internal also got increased by 1, right? Internal also got increased by 1. Okay, in this tree, the moment you make the leaf also by 1, okay, here the internal basically not getting increased, that's fine. So leaf got increased, right? So basically, you can say in this case also, if it is like kind of full, where the internal nodes are less and leaf nodes are more, okay? So Here in this case, the number of internal nodes are 2 and leaf nodes are also 2. But leaf are not exceeding, okay? Obviously, like leaf cannot exceed the internal number of nodes. Why that is the case? Because internal number of nodes plus 1. Because the moment you make the leaf node, okay, see, currently you are increasing internal only, because first you have to increase the internal, okay? The moment you increase the internal at this particular point in time, leaf has not got increased. Earlier also this was leaf, one leaf, I mean, here also it is leaf, but internal got increased, and now later on leaf get increased. Okay, so basically internal first, internal has to increase automatically, right? And then leaf will increase. So leaf will always be less than equal to internal, right? And total number of nodes that we already know, this will be 2 power h plus 1 minus 1 and h plus 1. We have already proved it. Minimum number of nodes and maximum number of nodes we have already seen. Minimum nodes, h plus 1, maximum nodes, 2 power h plus 1 minus 1, right? Okay. Internal number of nodes obviously has to be greater than equal to h, or whatever is the height, this has to be greater than equal to h, because everything is internal. Okay, it has to be at least h. Okay, then only it will be internal, because till this point it will be everything is internal, right? Till the, see, if this is the height, so everything is internal, so it has to be at least h. Okay, whatever is the height, so internal nodes has to be at least that much. Okay, because height also start with the 0, right? Height also start with the 0. So here the internal nodes are 3, and if you take the complete skewed tree, okay, so internal number of nodes are also 3, and height is also 3. So basically height anyway has to has to be less than equal to internal number of nodes, and internal number of nodes has to be less than equal to, if you take all the nodes till h minus 1 height. So basically these are the nodes till h minus 1 height. Maximum nodes till h minus 1 height. Okay, so internal nodes has to be less than equal to the last level. Okay, at the last level it has to be, at most these could be internal nodes. So maximum number of internal nodes could be whatever could be the height h minus 1 nodes. Okay, so at height h minus 1 you can have this. So basically that's why also this is also true, this is also true. Understood? So basically ABC are true and D is anyway false, we have seen with the counter example. But let's just also see what they are saying. Height is less than equal to leaf. Okay, so actually there is no as such relation that leaf and height should be less than equal to like this, and leaf is less than equal to 2 power h minus 1. No, maximum, as you know, the maximum number of leaf could be even 2 power h, right? We have seen maximum number of leaf could be even 2 power h. Okay, if it is like this, okay, maximum number of leaves could be 2 power h. So D is false. Okay, so yes, A, B, C are the answers. Okay, so now there are some questions which are having actually the code. Okay, if you're gate DA students, then don't worry. Like this is actually just like a pseudo code. I mean, this is C code, but you can treat it like a pseudo code. Okay, I will do a quick analysis of these codes. These are very easy questions. Okay, very easy questions. If you are even gate DA students, then also it's fine. There are, I think, not much questions. 1, 2, 3, 4. Okay, 2, 3 questions they asked. Let's just quickly see these questions. Okay. So consider C program. So basically this some program is given. They are saying that do something is basically doing what? Okay. So you notice one thing here is that they are saying if PTR is not null, then you do something. Okay. If PTR left child is not null, then go to the left child and 1 plus that. Okay. If right child is not null, then go to the right child and 1 plus that, and 1 and maximum of these two. If you're taking the maximum, then are you counting something? Does maximum count something? Can you say using the maximum, can you find out number of leaf nodes, number of nodes, number of, no, right? Number of anything you cannot find out. So it must be the height. Okay, because the maximum operator is being used. Okay, so that is why it must be the height. And it is very logical. If left child is not null, go to the left, and whatever is the height you are getting here, okay, left height plus 1. So maximum height you are taking, because the actual height will be the maximum height. So value will be basically, this value is coming from above. Okay. So you are anyway taking the maximum height. So using the maximum operator, obviously you cannot find out the number of something. So that's why D is the answer here. Okay. So D is the correct answer. Let's see this. This has been asked in GATE 2007. So what they are saying, consider the C program, binary tree. The value written by the get value when a pointer to a root of binary tree is passed as an argument is. Okay. So they are saying what this get value is doing. So let's just check it. If left child is null and right child is null, so you return 1. Otherwise, you add. Now they're not taking the maximum, now they're adding. Okay. Get value left child, right child, left, right. You're adding both and then value. Okay. So I think you're adding both. So number of nodes in the tree, number of internal nodes, number of leaf nodes. It cannot be the height, by the way. Okay. Now you tell me it is what? So you can see if left and right both are null, right? Then the value is 1. So actually it is getting satisfied in all the cases. Suppose one of them is not null. Okay. If left is not null, right is not null. See, it is definitely not counting the leaf nodes, right? It is not counting the leaf nodes or something. See, for the leaf node, it is saying 1. It is counting the total number of nodes because it is not filtering based on the internal or something like, right? So if it is at the end, if it is leaf, then they are saying okay 1. Okay. Otherwise, it is basically left nodes and right nodes. So total number of nodes they are counting. Okay. Sorry, they're counting the leaf nodes. Is it? So answer is C. Okay, you see the base case. Okay. So they're returning 1. When only it is leaf. Yes, that's a tricky question basically. Not that tricky actually. If you are familiar with these questions, you should be able to do it. So they're returning 1 whenever this is a leaf. Okay. If this is not leaf, if this is internal node, then they are not basically adding its value. They are just saying okay, go to the left or right. Okay. If it is internal node, they are not incrementing anything. They're just saying go to the left or right. And now this value plus could be confusing. Actually, this value plus doesn't make any sense here because value is anyway 0. Okay. Value is anyway 0. And this is a local variable. Okay. For the local variable, this value plus is just confusing you. Okay. So you can even remove this value plus because value is anyway 0. Okay. And this is if and then this else. So if it has not been into the if, then only it will be in else. So this value plus is actually confusing you. Okay. You can just remove it. And this is basically going to the left and right, just adding left and right. This is not adding. If it is plus 1 also, okay, if it is plus 1 also, then it will be the total number of nodes because you're counting itself and then you're going to the left and right. Okay. If you're not counting itself, then it is no plus 1. Okay. If it is plus 1 also, then it will be total number of nodes. Currently it is number of leaf nodes only. Is this clear to everyone? Okay. So I hope that's fine, right? Let me know if there is any doubt in this. Okay. So basically this value plus was confusing and also it is not plus 1. If it is plus 1, then it is total number of nodes because it is counting itself and then going to the left and right. Okay. Let's see this question. What they are saying. If they are saying that longest path in the tree, then they want to actually compute the height. Okay. This function wants to compute the height. I think height we have already computed. Yes. So height like this also we have computed that okay maximum of whatever is coming from the left 1 plus left or 1 plus height and you can take the maximum, right? Height we have already computed, but let's just see what they are saying. Okay. Left is null, and right is null also, then return 0. So else this is the case where left is null but right is not null, right? So this is the case where left is null but right is not null. Okay. Else, so basically they are saying if both are, if that is null then it is -1. If left is null, left equal null. If right is also null, then 0. If right is not null but left is null, then this. Okay. Else, else means if left is not null, then go to the left. Okay. And if right is null, then you just return the height from the left, which is fine. Okay, 1 plus that. Okay. If right is also not null, so this is the case when both are not null. So what should be the answer? See, in the height, they're at the time of return, they are doing 1 plus, which is fine, which means, um I mean, these two should not be answered. I mean, for the B2, actually, at the time of return only, they are saying whatever you are getting. Okay. See, S2 is the height that you are getting when both are not null, right? But you have to do 1 plus. H1 is the height that when you are getting when left is not null or something like that, right? Okay. So basically, you have to do 1 plus whatever is the maximum. So either this is answer or this is answer. For the B1, can you tell me, will it be 1 plus or without 1 plus? You have to do 1 plus actually, right? So for B1 also, left is null and right is not null. And then you're basically calling the, if right is not null, you will be basically calling like this. And then what 1 plus, right? Anyway, the base case is anyway -1 for that same region. So A is the answer here. Okay. A is the answer. You just have to analyze this question. So basically they are saying that that at the time of return, so this is the hint that they are giving, that at the time of return you are doing, see, this particularly this height function is not including that particular node itself. Okay. So at the time of return you are doing 1 plus. Okay. And for the leaf they are saying the height is anyway 0. Okay. I mean their height is anyway -1. So if leaf is having height -1, so this will be having if you are calling with this, okay, let's suppose this is the only tree, so this will return -1. Okay. And sorry, not this will return I mean, not for the leaf. If it is null, then this will return -1, but it won't be impacted. And this will return what? This, since this is just one node. Okay. So for this left and right will return -1, but it will be plus 1 plus. So it will return 0. So from 0 and -1, you will do +1. So maximum is 0 and then +1 is basically 1. So for this particular tree, the height is 1. Okay. This is a little tricky question, I can say. See, unnecessarily they are complicating it. To find out the height, it is very easy to find out the maximum like this. Okay, we have just done the height. But if you are having the complicated code also, then also you can see that how to check it. And what is the best way to solve these kind of questions? The best way is that you just have a simple tree. Okay, just have a simple tree. For example, I think, yeah. So here also they are not giving with the example, but you can have a simple tree and then you can call. Okay, you can call with the or maybe I think this tree will also be doing the fine. Okay, you then you can call the function and then you can see what it is returning. See, here they are saying if left is null and right is something, then it will be basically like this. If right is null, then you directly return. Okay, so in this case nothing is null. Anyway, like I hope you understood the point, right? If right is null, then you just return 1 plus whatever is the whatever you're getting from the left. Okay. If left is null, then 1 plus whatever you're getting from the right. Okay. 1 plus whatever you're getting from the right. Okay. Let's see this question, what they're saying. Maybe I can just go to the next page. Okay. So they are saying that if I have this function and if foo is called with the pointer to the root node, then what it will print. Okay, they're asking what it will print. Let's just check it. So if p is null, then return 0, else p val plus left plus right. So this value is 10. Okay, so it will say that, okay, 10 plus whatever is left is returning and whatever is right is returning. Then it will print. Okay, so left will go, and for the left also you will say its value plus whatever left is returning, whatever right is returning. Now if it is 3, okay, so left right will return 0 0. So here the first thing that we will print is 3, right? And then basically left and right, so it is calling left and then right, right? And the second thing it will print is 8, because 3 will get printed and 8 will get chance to print. Now, since 3 and 8 will return at this point, so 3 will return what? 3 will return whatever it is printing. 3 will return 3. So 8 will return 8. So 3 plus 8 plus 5 will get printed here, which is 11 plus 5, which is 16. So 3, 8, 16, something like this. So I think C is the answer, right? 3, 8, 16. Okay. So it is easy question. So where is the answer written here? Okay. 3, 8, and then 16 will, yeah, 3, 8, 16. Okay. So C is answer. Understood? So that's very easy question. So they are saying that, okay, left is this. It will call left, right, whatever left return, whatever right return, and then its own value. So basically, first thing that it will print 3 only, because 3 is the base case here, right? 3 and then 8 and then 3 plus 8 plus 5. Okay. So that's how it will do. Understood? Great. So that's all about the binary tree. So we have solved, let me just tell you, we have solved all the questions of the binary tree, which were tricky questions. Okay. 1, 2 we might have left, but most of the questions we have solved. Gate PYQs. Now we will do binary search tree as next topic. Okay, this is the next topic. This is very tricky. This is actually very tricky. Okay. This is very tricky. Okay. These questions generally they ask very tricky questions from binary search tree. Okay. Many times they ask very tricky questions from binary search tree. So that's all for today, and let's just meet tomorrow. So tomorrow we will be doing the binary search tree. Okay. Let me write it here. So just a small request that if you are liking the session and if you are enjoying, then please just share the session. Please hit a like button and just share the session with as many students as possible. And then we will be just continuing the series. I will be just starting. I have just started with the binary tree. Then we will go to binary search tree, and then there are many other interesting topics or challenging topics, and we will be covering almost all the gate PYQs from data structures and algorithms. Okay. So just hit the like button. That's all. Thank you so much, everyone.